These diagrams here are focused on the interaction between the water molecules and the ions in ionic compounds. A water molecule H2O has an oxygen that is slightly negative and the hydrogen side of the molecule are slightly positive. And the molecules will orient themselves and create a strong ion dipole attraction between the ions and the water molecules. So in this diagram here, they're modeling an ionic compound that's dissolving. So you can see the lattice and the water molecule is coming in and attracting to the positive ion and to the negative ion. And eventually, at the molecular level, what you would see is the positive ion surrounded by water with the oxygen pointing towards it, and the negative ions surrounded by water with the hydrogen end pointing towards it. Now, these are constantly moving and the interactions are constantly being formed and constantly being broken. But the idea is that for the water to dissolve the ionic crystal, the water molecules need to be able to surround it. And like we said before, there needs to be some kind of a positive interaction between the solute and the solvent. This is just highlighting a few different ways of looking at it. In the right-hand side over here, we see this is kind of a three-dimensional view of the ion dissolving. What we want to do, though, is look at our three types of molecules, so our polar, our non-polar, and our ionic crystals, and put them in order of increasing solubility. So when we think about non-polar solutes, okay, we've talked about before that they will have no slightly positive or slightly negative charges on them. And so the water molecules, and I'll use these little diagrams to represent my water molecules with the point being the oxygen. The water molecules are more attracted to themselves than they are to the non-polar molecules. So they will stay separate. A classic example of this is oil and water. If you put oil into water, it'll just sit on top because the oil molecules are more attracted to other oil molecules than they are to the water molecules. For polar compounds, when we think about them dissolved or polar molecules dissolved in water, what we want to remember is that a polar molecule itself will have a slightly positive and a slightly negative end. And that will allow the water molecules to surround it. So if there's an attraction, so the oxygen end will attract at this part of the molecule because it's slightly positive, while the hydrogen end or the slightly positive end will attract this end of the molecule because it's slightly negative. So what we're looking at here is a nice small molecule that's slightly positive on one side and slightly negative on the other side, and how the water molecules can surround it and attract it and therefore dissolve it. We'll talk about how polar molecules will have a variety of level of solubility, but for now, when we are given a polar molecule, we can predict that it's likely going to be at least somewhat soluble in water. Lastly, our most soluble out of the group are our ionic compounds. Okay, and that is because we have our positive ions and our negative ions. And the positive ions will be surrounded, forming an ion dipole interaction with the water molecules, and as well the negative ions will form an ion dipole interaction. So this is a more simplistic view of the more complex diagrams that are above, but it's showing the same principle. Okay, and this will also lead us into our discussion of conductivity. So as you know, ionic compounds will not be conductive as solids, but when they're liquids or when they're dissolved in water, they will conduct electricity. So let's have a look at that. Okay, so this is a great visual here of a conductivity apparatus that's connected to three different scenarios. So on the left-hand side, we've got our conductivity apparatus connected to distilled water, and we see that the light bulb is not on, so it's not conducting. We've got it inserted into some solid sodium chloride, okay, and it's zoomed in on the crystal lattice here, and then it's inserted into a solution of sodium chloride. And so the only case here where we're seeing it conduct is when it's in solution. And it's because of these free ions that we are able to conduct electricity. Okay, so when we set up the apparatus is trying to pass electrons from, there are basically these, in here, there are these two electrodes, okay, connected to our light bulb, and the electrons are being passed through. They're trying to get to the other side, and you can think of the ions as basically shuffling the electrons along. Okay, so it'll allow for the conductivity apparatus to work. The key is that we need free ions. So ionic compounds, when they're in solution or dissolved in water, will conduct electricity. And then the other way that we'll see free ions in an ionic compound is in the molten liquid, which is just, we call it molten when the ionic compound is melted. It's usually at a pretty high temperature because we've already talked about the fact that ionic compounds have such a high melting point. So in this case, with the ions in their fixed positions in their lattice, they're not free to move, and so it won't conduct. Okay? And then distilled water is made up of just water molecules. There's no ions in the solution, like there might be in tap water when we think about there being minerals, which are really salts or ionic compounds dissolved in water. So there are no free ions, so it doesn't allow for conductivity. And this also gives us an opportunity to talk about what an electrolyte is. So an electrolyte, Gatorade as an example, you hear in your everyday life of electrolytes. And so when people are taking Gatorade to act as an electrolyte, or if you're somewhere and you're dehydrated and you need to take electrolytes, you're trying to replenish the salts that have been lost through sweating. So from a chemistry perspective, those same salts is what we're referring to, and we call an electrolyte something that conducts electricity when it's dissolved in water. So ionic compounds are electrolytes because they conduct electricity when they're dissolved in water. Non-electrolytes, on the other hand, are compounds that do not conduct electricity when they're dissolved in water. So something like sugar, okay, which is a molecule, will dissolve in water, but it doesn't conduct electricity when it's dissolved in water. Okay? There are no ions in the solution. Our last example for conductivity is metals, and we've talked about these already, but it comes back to these structures. We always want to connect to the structure. What is it about the structure that gives rise to the properties we're observing? Okay? In a metal, you want to imagine those positive nuclei, and then there are these free moving electrons through the sample. So if I'm trying to conduct, if I send electrons into a wire through one end, they're able to be shuffled along through the crystal because the electrons are mobile. The last piece that we would want to look at is this summary of properties. So we've talked in detail about the properties, and when you look at a table like this, it's tempting to feel like you should memorize the entire table. But more importantly, what you want to do is connect to the structure and make sure you understand why each of the properties is what it is. So I'm just going to put at the top here so that we have it in context. When we think about an ionic compound, we automatically want to think about that crystal lattice. When we think about a polar molecule, we always want to think about the fact that there's that slightly positive and slightly negative. So if we want to think about interactions between them, we've got two of them. And then for polar molecules, we've got our molecules that have no noticeable slightly positive and slightly negative present. Now, this table, okay, you might remember from earlier on in the unit, the beginning of the unit, we were only categorizing things as being ionic and covalent compounds or molecular compounds. And through our investigations, we noticed that covalent compounds needed a further point of comparison. We needed to divide them up a little bit more because it was too big of a category. And one of the main things that we noticed was that there were these groups of molecules that didn't dissolve versus they did dissolve. And that's really kind of our main point of separation between nonpolar and polar at this stage. Nonpolar molecules will be soluble in other nonpolar substances because they will have better interactions with them, but they won't have interactions with water. Okay, so we'll just do a quick walkthrough because the reality is we've gone through each of these in detail. Okay, but what we want to do is connect back to the structure. Okay, so remembering that with that ionic compound, they tend to be solids. There's a strong attraction between the ions. We refer to them as being crystalline because they tend to be very organized in their structure. Okay, their melting point is high because we need to overcome this strong attraction between the ions in order to separate the ions and melt them. Okay, we refer to it as overcoming the lattice energy when we describe it. For solubility, we talked about how ionic compounds tend to have high solubility, and that's because of that strong attraction to the water molecules. Okay, because water is polar, so there's a nice attraction between the positive and negative ends of water and the positive and negative ions. For conducting electricity, okay, they conduct electricity as both a liquid and as a solution because of those free ions, but as a solid, they won't because the ions are in fixed positions. Okay, so you can see it's not something you need to memorize, but something that you can use the structure to help you to remember and stay connected to the structure. For polar molecules, it's more difficult to predict their state at room temperature because there's going to be such a variety of the different types of polar molecules, but they do tend to be liquids and solids. So they have sort of medium attraction between the molecules. It really does depend. Okay? You learn more about that in future courses. Their melting points tend to be lower, so we're kind of doing a relative scale here. So because the attraction between the molecules is between that slightly positive and slightly negative, those intermolecular forces are going to be weaker than what we need to overcome in our ionic compounds. So they'll tend to have lower melting points. Their solubility is going to be a little bit lower because the attractions are not going to be as strong to water as with ionic compounds. And they won't tend to conduct. Okay? And this one here, this sometimes slightly, okay? We put sometimes slightly in senior one chemistry, you will, it will always be a no. Okay? So you don't need to worry at this stage that there are some molecules that will conduct electricity when they're dissolved in water, or they will be electrolytes. We'll learn about those in future courses. Okay? We just like to make sure that we're giving you correct information at this stage and not saying that they never conduct electricity. Okay? Then for non-polar molecules, they will tend to have weaker intermolecular forces because there is a weaker attraction between the molecules. So they'll tend to be gases, they'll tend to have lower melting points, they'll tend to not be soluble in water because they won't have strong attractions to the water molecules. Okay? And they won't break apart into any ions. Okay? They're not going to dissolve, so we're not going to have conductivity in those cases. And when they're liquids and solids, there's not going to be any ions. Okay, so that wraps up properties. Hopefully you have a better understanding of the relationship between the crystal structure and the properties.